Hello, everyone, and welcome to this talk about QEMU, the Linux and the ugly that I'm going to present to you with Jacob Haas. Let me introduce myself. I'm Omar from ESP-IDF core team. I implemented the ESP32C3 support for QEMU before I studied at the University of Paris Diderot in France. I worked on safety critical RTOS and BSPs before, and then I joined Espressive in 2020 to be part of ESP-IDF core team. I wrote several emulators in the past, hence my implementation of the ESP32C3 in QEMU.
Yes, hello. My name is Jakob, or Jacob, however you want to call it. I studied computer science and I joined Espressive in 2019. Before I worked as an embedded Linux developer. And when I came to Espressive, I noticed that there are some workflows that would probably be much easier if you run them on the host, such as certain kinds of unit testing, for example. And this is how I initiated and began to drive this Linux target project that I will introduce later.
So let's start. We are going to present to you the difficulties of testing and development with ESP-IDF. Then we will present the QEMU target, QEMU emulation for the ESP32C3. Then the Linux target for IDF. And finally, we will give you some guidelines about which one to choose. So first of all, let's see the difficulties of testing and development when writing an application with ESP-IDF. The first difficulty that you will meet is that you will need some extra hardware for debugging your target, and mainly for JTAG. Of course, if you use JTAG, you have to use OpenOCD if you want to manage the communication and manage the debugging session. Every time you modify your project or your application, you will need to flash it to your board. So you only have a single application that can exist at a time. Flashing is rather slow, and it also wears out the SPI flash, since SPI flashes are limited in the number of write cycles. Another limitation that you will encounter is the limited hardware breakpoints that you have on a single chip. And of course, the debugging runtime is different than the regular runtime. I'm sure you encounter some situations where when you encounter a problem, a bug, an issue in your application, then you try to debug it with some printf or with a JTAG, then the bug disappears. And this is because of different timings. Finally, if you are using ESP-IDF and you are trying to run it in a CI or running some tests, you will have some limited number of hardware, limited number of targets. And this is where the Linux target or QEMU can help. Let's see how to do this, how to debug with QEMU and how it can help you. So what is QEMU? QEMU is a free and open source emulator, or what I like to call an emulator framework. It was written in C, and the latest release is from June 2024, so it's very recent. It works with several modes, including user mode emulation, hypervisor, and the one that interests us the most, the system emulation. In this mode, it can emulate a whole system, a whole computer, with all its peripherals, even if it's a different architecture. And this is what we use in Espressive to emulate the ESP32, and in this case, ESP32C3. So first, let's see how an emulator works, a classic emulator works, I would say. So the first thing that the emulator does is open and load a binary file, which contains the code and data. Then it will read this file instruction by instruction. It will interpret each instruction. So for example, if on RISC-V we had the add instruction, add x10, x1042, it will be interpreted as we have an array of virtual registers and we just add 32 to the 10th one. Then if we have any IO-related input or output, we will have an emulated UART, for example, or an emulated timer group, or even RNG to generate a random number generator. But it means that we will monitor every memory read and every memory writes. So that was how a classic emulator works, interpreted emulation. But the way QEMU works is different. QEMU does dynamic recompilation. So the beginning is the same. We open and load the binary file to emulate. Then we read the instructions. But the first thing that it will do is it will compile a block of arbitrary size into the host architecture. So for example, if we take back the RISC-V instruction add I, it will be compiled to an x86 instruction if your host computer is using x86 architecture. And it will do this for a whole block. And after that, it will execute the compiled block. And if there is any I/O device that is written to or read from, QEMU will exit this compiled block, and it will execute some code that you have to write in your emulation framework, in your target implementation. But then this is the same thing as the interpreted emulation. So it means that we will have an emulated UART. We'll have to emulate every I/O register of a UART, in this case. But we can also have timer groups, and we'll have RNG. And once we finish emulating the read or write of this I/O register, we will go back to the compiled block, and this process will continue again and again. So what are the advantages of using QEMU? It's fast. It provides very fast emulation thanks to recompilation. For example, this small snippet of code, which does a sum, the example is not very useful, but it's just for the sake of comparison. On the ESP32C3 at 140 megahertz, it takes 6.77 seconds to execute. But on QEMU, on my computer, which uses an x64 CPU, it takes 265 milliseconds, so it's much faster. Using QEMU will also help you debugging applications. It even supports ESP-tool.py, which means that you will be able to flash the emulated NOR flash directly with ESP-tool. Of course, it will ease automatic testing and even fault injection, which is much harder to do on real hardware. And it can even emulate critical peripherals like eFuses, flash encryption, RSA. And this is very useful for eFuses because on the real hardware, if you burn some eFuses, then you cannot unburn them. But you can do this with QEMU. That's not an issue. And finally, we can emulate some peripherals that are not present or does not exist on the real chip. For example, for the ESP32C3, we added an LCD frame buffer, which can show a GUI, which is harder to do on a real chip. Okay, but what are the drawbacks of using QEMU for development? Well, the IOs are pretty slow. Same. So here in this example, we will read the UART RX FIFO length. This takes 7.5 milliseconds on the ESP32C3 on real chip. But in QEMU, it takes almost 32 milliseconds. So it's much slower. And this is due to the fact that whenever you have an IO, you need to exit the compiled block. So this adds an overlay. This adds an overhead. Also, you have the OS latency and abstraction layer. Let's say that, for example, one of your peripheral needs to access a file. So you will need to use the Linux API if you're running on Linux. And so you will have the whole kernel layer abstraction that will add up every time you have an IO. Also, it's not time accurate, or it's more like not cycle accurate. It's impossible to know exactly how fast a program will run on a real hardware if you only execute it in QEMU. There is the iCount parameter that lets you reduce the disparity of execution time between different CPUs and different computers, but that's still not cycle accuracy. Of course, if there is inaccurate peripheral implementation, this will lead to very challenging bugs. So if you don't properly emulate the UART or the timers, you will have very weird issues in your application, and this is very hard to debug. And finally, setting up a new chip, implementing a new target is quite challenging, mainly when you see that there is not a lot of documentation for the code, for the core code of QEMU. And even sometimes the code inside QEMU is not very well commented. It does not also emulate the SPI, I2C, and any other bus that has some signals, because as I said, it's not cycle accurate. So for example, if you have an SPI read or SPI write in your emulated SPI device, you will just have a function that is called with the buffer of the bytes that are sent. That's useful for very simple emulation like a NOR flash, but if you really want to see all the signals on the bus, that's not possible. So what do we have today on ESP32 in our ESP32C3 targets? So we have all the core features. So we have RAM, we have ROM, we have external flash, and even flash cache. On ESP32, we have dual core CPU, which is supported, and this can also use 2 cores on your host computer if you have multiple cores, of course. It is possible to use a custom ROM file. We have the security features that are implemented for both targets. We also have some fake devices, as I said earlier. We have an RGB panel with extended RAM for the C3. We also have an Ethernet controller, since there is no Wi-Fi emulation yet. We can use the Ethernet controller to have access to the network. There are still some features that we would like to implement, like I2S for sound support. But it's already usable. QEMU is already usable for both targets for most of your use cases. So how to quick start with QEMU for IDF? There are some pre-built binaries for both ESP32 and ESP32C3. It's possible to use IDF tools.py to install them, as you can see. Then you only need to compile your IDF project as if it was for the real target, because IDF is not aware of QEMU in the sense that when you will compile your application, it will just be like for the real target. And finally, instead of using idf.py flash monitor, you can just use QEMU, and you will see the output that you have on the right. And this will be executed in a new environment, so a new flash with new if uses. So if you're in your application, you burn if uses, you can just exit and then rerun idf.py QEMU, and you will have new if uses, and you can try again. So you also have a more advanced usage and debugging. So it's possible to make the environment persistent. Let's say that you want to create an emulated NOR flash and want to flash some data to it. You want to exit the emulation and take it back later with the same data that you wrote. It's possible to do this. I will not go through all the options here, but you can specify some binary files for both the NOR flash and the if uses. And it's even possible to attach a GDB client to the running target. And thanks to that, you can also run GDB as what you would do on the real target with OpenOCD. The only thing that changes here is the remote port. You can find all the features and the command line options in our GitHub repository, which is ESP toolchain docs. And this is a small demo that I would like to show you. So on the left, I compiled a small ESP32C3 example. It's a hello world example. It's running in QEMU. And on the right, it's a GDB attached to this QEMU instance. And as you can see, we can see the whole source code on the right. We have the app main. We can put breakpoint, and we can even go through all the variables that exist in the system. And that's very fast and easy to set up. Okay, but in some cases, QEMU might not be what you would like and might be a bit too close to the hardware, and you may want to test something that is a bit higher on a higher level, like an algorithm. But I will let Jacob explain in more details this part.
Thank you, Omar, for this in-depth introduction into or insight into QEMU. And I am now going to cover something else, which is called the Linux target. What does Linux target actually mean? Well, it means that you want to run an ESP-IDF application or ESP-IDF code on the host machine. In particular, you want to run code that uses ESP-IDF APIs and the FreeRTOS APIs on the Linux host machine. The goal is to have to build an executable application or ELF file on Linux, and this can be run directly. And it will be produced into the build directory. One note here is that despite the name Linux target, it also runs on Mac with some limitations. The reason why we are doing this, why we want to run code on the Linux host machine, native code, is that it has several advantages. First of all, there are many debugging tools readily available on Linux. Usually you just can easily install them, and then you can start debugging very deeply and efficiently. This is, for example, GDB, Valgrind, strace, and others. You also do not have any uploading overhead. So applications run immediately, right? There's nothing to flash here. Another advantage is that applications on the host run much faster than on ESP32 series chips. This is particularly useful for large batteries of unit testing or unit tests, where each test runs one after another without any delay or timing requirements. There's no hardware necessary, as in the case for QEMU, which is quite useful if you run out of development boards or somehow do something bad to them. One thing that I think is not to underestimate is that the automation overhead in CI/CD systems and similar setups where you need automation is much more reduced compared to run code on an ESP32 series chip. The setup is way less complicated. You don't have any hardware or communication channels to hardware that may break, that may have issues and whatnot. We also try to keep the tools or the commands to run code on the Linux target fairly similar to ESP32 series chips, as you will see later. In general, there are two approaches to implement the Linux target. One is using mocks, CMock in our case. CMock is the mocking framework that we use in ESP-IDF. The other approach would be to use a kind of simulation that simulates FreeRTOS scheduling. And we will go over both approaches now. When you use the mocking approach for the Linux target, so for running code on the host machine, it basically means that you mock most, if not all, the dependencies. So basically the only, in a way, original code that you run is the code that you develop or test. And everything else is not the original code, but is mocked. So what you need to do is you record all required behavior to the mocks so that the mocks later will know how to behave when the actual code runs, the actual code that you want to test or run or develop. You still have the native libc available, even with the mocking approach. And what you need to remember is that FreeRTOS APIs are mocked as well. So if you call, for example, xtask create, it will not create an actual task in the background. It would just expect some values and then return. It's very, very simple, but nothing else will be done in the background. So this is something you need to remember. So you cannot use the mocking and then try to create a FreeRTOS task. That will not work. Let's look at a simple example, like a simple use case. We have some unit test case here that tests the hypothetical function QHandler, which takes a QHandler as argument, and it is supposed to eventually call UXQ message waiting, which also takes a QHandler as argument. So what you would do in a unit test, in the test case would be you first initialize the Q handle, so the variable Q in this case. Then you call this function uxQ message waiting expect and return. And this is the function that from the name already you can see that is supposed to record the mocking behavior of the function that will later be called when the code calls uxQ message waiting. And in this case, what it does, it records the current value of the variable Q as the value that should be expected, and then return return 2 in case it's correct. Later, you call the function itself, the Q handler function. So this is now where you call the original code. And while Q handler is running, it will eventually call the uxQ message waiting function. But behind that, there will be the mock, and it will check if the Q handle is called is passed correctly. And if so, it will return 2. And then the Q handler function is supposed to react accordingly to the return value returned by the mock. If for any reason the Q handler function or the code behind it would not call the Q, will not pass the Q value correctly or pass something else, then the mock will basically trigger a unity assertion and print out a meaningful debugging message. So you will see what the value that that expected, what the value that has been expected was, and what the actual value was. You can probably already see this is pretty useful for unit testing or like rather low-level unit testing, but it's not very useful for larger simulation or system tests. Because in that case, you would record so much behavior to the mocks that it would quickly become infeasible, right? Why we have something called the POSIX Linux simulator. The POSIX Linux simulator is an upstream FreeRTOS project, and we integrated it into ESP-IDF. And what it basically does, it simulates FreeRTOS tasks and the related scheduling. Underneath, there will be p-threads for running the tasks, but more on that later. And the simulation of the scheduling is done the following way. So we have, let's suppose we have two tasks, task 1, which is currently running, and task 2, which is currently ready. So it's about to be run and should be scheduled next. So on an actual ESP32 series chip, there would now be a tick interrupt. But on the POSIX Linux simulator, we use POSIX signals. This POSIX signal will come and interrupt the task 1. It will go into a signal handler and then notify task 2. The way the notification works is that it's based on condition variables. So every simulated task has its own condition variable, and this is used for tasks to wait and being notified when they are supposed to continue running. So the task 1 will notify the condition variable of the task 2. And then for a brief moment, so the most important thing now is task 2 is runs now. And for a brief moment, both tasks run in parallel, but not for long, because then task 1 will quickly go into the wait on its own condition variable. And in the end, task 2 is now running and task 1 is not running. So the reason that task 1 knows to notify task 2 and not any other task is that the actual FreeRTOS code responsible for scheduling is still run. So in the POSIX Linux simulator, only the port layer is exchanged, but nothing else. So the actual task that, the actual code that runs to determine which task should be scheduled next is still run. Besides this simulated scheduling of FreeRTOS tasks, there are also a bunch of components in ESP-IDFs that are simulated. Maybe simulated is not the very precise term here, because our main goal is that we run ESP-IDF applications without needing to use too many if-defs in the code. So sometimes the results that are returned from APIs or the actions behind are not really a good simulation, but it's meant as a reasonable replacement so that you can run high-level applications, right? Again, the POSIX Linux simulator and the Linux target are meant for high-level applications and not for any low-level kind of simulation. In the POSIX Linux simulator, you can also still use the native libc. Of course, you can try to allocate a lot of memory there, but that will probably not work on an ESP32 series chip. The combination of the POSIX Linux simulator and mocking is still possible, which is quite advantageous in some testing and development setups. Another note is that some components may never be simulated. This is the case, for example, for drivers, because there's basically no meaningful way to provide anything useful for users who want to run high-level application on the host. Let's look at this example. It's a simple app main method. It will print hello world. It will print some kind of countdown afterwards, call vtask delay, the FreeRTOS API. And finally, it will call restart, basically. This code runs on both the Linux target as well as on ESP32 series chips. The only difference here will be that calling the ESP restart function on an actual ESP32 series chip will actually restart the chip. On the Linux target, it will just end the application because we haven't found any meaningful way to simulate restarting, and it's probably not very useful anyways, because the applications that we want to use for the POSIX Linux simulator, they are very high level. So when we want to build and run code on an ESP32 series chip, we usually do something like this. You might be familiar with this. It's idf.py set target. That's the target command, and set it to ESP32 in this case. It will set you the target. Then you call idf.py build flash monitor, and the application will be built, flashed, and monitored. If you want to build and run applications on the Linux target, you first of all need to use the preview switch for the set target command, because the Linux target is still in preview. Then it will set the target like for any other chip. Then you call idf.py build monitor. There's nothing to flash here, so you do not need the flash command. When you run the code, then on the chip, you would see something like this. There's some startup message, and then the output of the hello world application, hello world, and then that countdown. If you run that code on the Linux target, however, you will only see one startup message, this port starting scheduler, and then the output of the application follows immediately. I also included the last lines of the ESP-IDF monitor output here, just for completeness. You would also see that if you run code on an ESP32 series chip, but way ahead. So there are some limitations for the Linux target that we need to consider. First of all, the behavior is not accurate. As I already mentioned, if you try to allocate 1 GB of memory using the native libc, it might probably work, depending on the system you're using, like the Linux machine and the limits you set. But it will never work on an ESP32 series chip, at least until now. The POSIX Linux simulator that we integrated into ESP-IDF has some other special limitations. First of all, the simulator scheduling is not FreeRTOS anymore, not FreeRTOS-like anymore. This is because, as I already mentioned, under the hood, a pthread will be created to run the code. Hence, the scheduling is still very dependent on the hosts on the Linux kernel, and that's the main scheduling driver here. So keep in mind it's not FreeRTOS anymore. Another issue is that the ones of you familiar with POSIX signals have probably noticed this already. We call certain functions from a signal handler, from within a signal handler. In particular, this is the condition variable related functions, and they are not signal safe. The outcome of this is that basically you can have situations where there's priority inversion inside the POSIX Linux simulator and following deadlock. This happens in particular if you call printf or related IO functions from simulated FreeRTOS tasks with different priority. So this is something you should definitely try to avoid. Whenever you log, try to use that only from one task and make sure that you never do it from different tasks with different priority. Another issue is that simulated FreeRTOS tasks can also block, of course, on native Linux functions, such as select, for example. This is a problem in particular if you have high priority tasks that are blocking, because the blocking is not recognized by the FreeRTOS simulator or by the Linux simulator. So you can have a high priority task that is blocking a lot of time or most of the time on select, for example, and thereby stealing away runtime from all the other tasks. This is something you need to consider. It's also an issue because the POSIX Linux simulator always simulates single core behavior and never simulates any dual core behavior. What you should never do is call native FreeRTOS APIs inside the POSIX Linux simulator from Linux native pthreads. This is just dangerous. It's related to the way that the simulator is implemented, but the important thing is here it will almost certainly lead to a crash, so don't do that. Okay, this is basically the end of the Linux target introduction. And we will now give you some guidelines to better understand which approach to choose in what situation. It's like which approach, for example, the Linux target or QEMU or ESP32 series chips. In general, there's a spectrum of code, right? We have more abstract code that's fairly generic, and we have some very hardware-specific code on the other side. So for the quite abstract and generic code, as a rule of thumb, probably the Linux target is a good solution when you want to develop and test code. If you have code that is more hardware-specific and maybe needs specific hardware APIs already, then this is probably a good candidate for QEMU, again, as a rule of thumb. And there are certainly cases where you have some very hardware-specific code, maybe depending on timing, that you can only meaningfully run on ESP32 series chips. So there's no way around that. QEMU here has a kind of special role. There's basically another dimension to it. For example, you can set on QEMU, you can set registers, you can set breakpoints on certain registers. This is something you cannot do on ESP32 series chips, and on the Linux target is a different architecture, so it won't be meaningful. So just keep in mind, QEMU has some special properties beyond this spectrum of more abstract and hardware-specific code. Let's now finish with some examples of when to use which solution. Let's suppose we have a JSON parser and encoder library that we want to develop or integrate into an ESP-IDF component. In this case, the Linux target is probably a good choice here because that protocol code is probably not dependent on any scheduling or any hardware specifics. So you can easily run that code on the Linux host. Our second example would be we have an application that uses eFuse, secure boot, and flash encryption and the related cryptographic peripherals. In this case, QEMU can be very advantageous because QEMU does implement eFuse and other cryptographic security peripherals. So you can go and actually develop your application on QEMU. In particular, the code that sets eFuses, because whenever you run secure boot and flash encryption, you have to set eFuses on the chips. But eFuses are only settable once. So if you have, for example, 100 development cycles or development test and verify cycles, and you do that on the chip, then you just basically waste 100 chips. On the QEMU, that does not happen. You just run QEMU, and it resets the eFuses at the next reboot of QEMU, I think, or depending on the setting. And then finally, you can still verify you should still verify your applications on the actual chip, but you will waste much fewer samples of ESP32 series chips. Okay, and our final example is we want to test the runtime of a particular software function or hardware peripheral function. And here we can probably not get around exclusively running, developing and testing the code on ESP32 series chips, because the runtime is not something that QEMU or the Linux target are able to represent accurately. So that's basically still the ugly solution, but sometimes you need there's no other way around it. Okay, this example finishes up the guidelines section and also this entire talk. So let's now go to the Q&A session, and thank you for watching.